case of equilibrium called solubility equilibrium. And this uses the solubility product constant, which is just a special application of the equilibrium constant. And it will be used to help us predict some information about the solubility of a compound. So let's just go back and think about solubility a bit. Most ionic compounds that we can think of containing alkali metals are soluble in water. So the alkali metals, remember, are those things in the first column of the periodic table. Pretty much any ionic compound that they can form is going to be soluble in water. A great example is your table salt. It's sodium chloride. It's an ionic compound with sodium, an alkali metal, and chlorine gas. It will more than 35 grams of it will dissolve in 100 grams of water. It's extremely soluble. We can dissolve a lot of salt into water. By contrast, there are other ionic compounds that are insoluble. Compounds that contain phosphate, sulfate, or carbonate ions tend not to dissolve in water. Here are just a table that summarizes the solubility rules for ionic compounds in water, and you can come back to this as a reference if you're looking at a compound trying to figure out if it will dissolve. What you do is you find out where it would fit in here. If it's a compound, this word salts here just means an ionic compound that contains group 1 metals, so metals from the first column, it's soluble. This is group 1 and ammonia, NH3. If it contains one of those compounds, it's most likely soluble. There are some exceptions with lithium, but not a lot. It's probably soluble. If it has any of these words in it, it's soluble, most likely. For our purposes, it's soluble. If it has the word sulfate in it, it's probably soluble unless it contains one of these. If it has chloride, bromide, or iodide as part of it, so any compound formed with chlorine, bromine, or iodine, it's probably soluble, with the exception being silver, mercury, and lead. If it has sulfide or hydroxide, it's probably insoluble. It probably doesn't dissolve unless it would have fallen into this piece as well, unless it also has one of the group 1 alkali metals. If it has some of the heavier group 2, it's slightly soluble. And the last one, if it has the word carbonate, phosphate, or sulfite, it is insoluble, again, unless it would have fit in this row as well, unless it contains an alkali metal or ammonia. So any compound you're given, you just figure out where it would fit in this chart. Does it have a group 1 metal? Does it have a sulfate? Does it have a hydroxide? And then once you find out where it fits, is it one of these special exceptions? And that's how you figure out if it's going to be soluble. And so that part figures out whether or not a substance is going to dissolve at all. Most of our insoluble compounds will actually dissolve a little bit. So these are said to be slightly soluble. If you think about, any chemical reaction, things want to react. The universe wants to have chaos. Atoms want to move and react. So even if something is generally considered insoluble, might one or two of the, numerous atoms break off and dissolve? Yeah, probably. So most are slightly soluble. And so we care about the solubility product constant because it's a better way to show just how soluble something is and to really be able to compare a number with more detail than that chart of general rules tells us. So to give you an example, silver chloride would have fallen into the insoluble compound. Let me go back to that table. It's a chloride, so silver chloride would have fallen here. We would have seen soluble unless paired with silver, and so that would have been considered insoluble. But a very small of it does dissolve in water, so we can look at that as an equilibrium expression. We've got an equilibrium here. We've got solid silver chloride being placed into water. Some of it is going to dissolve. Some of it's going to break apart into ions in water. Notice here we've got that two-headed equilibrium arrow. The top one is drawn a lot smaller, just to sort of visually indicate this relationship, that there's a lot more of this than there is of this. This reaction going forward is pretty small, but it is still there. We still have an equilibrium between the solid and the dissolved ions. It's a pretty small equilibrium, but it's still an equilibrium. And so we can still treat it like any other equilibrium expression, and we can write an equilibrium constant for it. We've got aqueous products, so we've got the concentration of the aqueous products over here. And note, here's where that solid and liquid info comes into play. We've got a solid reactant. The concentration of a solid, like I said, is pretty meaningless, so it doesn't matter in our equilibrium expression. We can just write it as the concentration of silver ions and chlorine ions. We don't need this piece down here. It's just 1. We can think of it as 1. So just like before, we've got an equilibrium expression for this. And if we knew these numbers, or if we knew the equilibrium constant value, we could figure out either how much is going to be present or what our value is. And when we compare the solubility of salts, we want to have this equilibrium constant because it's much easier to compare like that. Is the equilibrium constant for one salt bigger or smaller than that of another? And that's a much easier way to determine if something is more or less soluble because we've got numbers to go off of. When we do this, we're working with the solubility product constant. That's how we refer to this special application of the equilibrium constant. And again, it's just going to be equal to the product of the concentrations of the ions, each raised to its coefficient. We leave out the concentration of the solid. We can think of it as just being 1. It doesn't matter for our expression. We just need our ions, our products, for the solubility product constant. If you have trouble remembering this, you can always remind yourself that solubility product constant product is part of this term. We just care about the products in the concentration. We just care about the ions in solution. So the smaller the value of this solubility product constant is, the lower the solubility of the compound. The smaller it is, the lower our concentration of products in our solution, and so the lower the solubility of the compound. Here's a table for your reference, just to compare the solubility product constant values for several ionic compounds that are considered slightly soluble to insoluble. And you can just come back if you ever need any of these values. Let's try an example. We would like to calculate the concentration of lead ions and chromate ions in a saturated solution of lead chromate at a constant temperature. And we're given the solubility product constant value. Let's see if we can find lead chromate on this table, if it was in here. Lead chromate, yep. Here's lead chromate. Here's its solubility product constant value. It's given here. So let's write a balanced equation for this reaction. We've got solid lead chromate that's going to dissolve to make lead ions and chromate ions. This will pretty much always split into 2 pieces. So we've got our cation, the lead, our anion, the chromate ion, and we've got it in equilibrium. So we know our reaction, we know our stoichiometry, and we know the value of our solubility product constant. We're looking for these two concentrations. Now, just like the previous lesson, the reason we need a balanced equation is because we need the stoichiometry. We need the relationship between the amount of lead ions and the amount of chromate. And we can see here that they're going to have to be equal, right? If just one molecule of this split up in water and dissolved, we'd make one lead, one chromate. We can't somehow make more lead than chromate, right? They're coming from the same compound. We have to have an equal number of each. Stoichiometry tells us the same thing. They've got the same coefficient. We're producing equal amounts of them. So, we write our solubility product constant expression. We know that all we're going to care about is the products, the ions, the things dissolving in our solution, the aqueous phases. The reactant we had was a solid. It can be left out of our equilibrium expression. So we've got this is going to be equal to the concentration of lead ions times the concentration of chromate ions. Neither of these had a coefficient in our reaction. They've got a coefficient of 1, so they've got an exponent of 1. And we know the value for KSP. The solubility product constant is 1.8 times 10 to the negative 14th. Now, we have to recognize that these concentrations are going to be equal. It's the only way we can solve this. So we know they're going to be equal. We just either make them both X or make them both lead or make them both chromate. Doesn't matter. They have to equal the same number. So here we're just solving for our lead concentration. Knowing that the chromate concentration is equal, we've plugged the lead concentration in for the chromate concentration because we know they're going to be equal. Now we have just one unknown and we're able to solve for it. Lead concentration times lead concentration would be the lead concentration squared. We can solve for this by taking the square root of both sides. This would be the same thing as just letting both be equal to x. We'd have x times x. X squared equals this number. Solve for x. So we take the square root of both sides. And again, we know that this answer here is the concentration of both ions. We know they're equal. And so we could plug those numbers back in to check our work, and we should get pretty much the same value of KSP we started with. Any differences can come from rounding. Alright, here's one, just a quick multiple choice question for you to try. Using this information that we've talked about, can you identify which of the following compounds is least soluble? So pause if you need, take a second to look at each of these compounds and pick out your answer. You should be comparing the KSP values. The least soluble compound would have the lowest KSP value. So you should have selected zinc sulfide as your answer because this value is the smallest here. 3 times 10 to the negative 23rd would be a 3 with 22 zeros in front of it before we get to our decimal point. That's going to be our smallest number. One more thing to take into consideration when we're talking about solubility is a neat little effect called the common ion effect. And this is important when we start mixing more than one solution. So we're dissolving more than one thing in our solvent. And we might run into a situation, say we're dissolving sodium chloride and calcium chloride. Well, we know sodium and calcium and chloride all dissolve, but each time we do that, when we dissolve both of those, we're creating some amount of sodium, some amount of calcium, but each one is contributing chlorine ions to the solution. So the chloride concentration is going to go up way faster than the concentration of the other two species. This is called the common ion effect. It happens when two or more substances that we're dissolving share an ion in common. And it has an interesting effect on the equilibrium and the solubility. Let's take a look at that same example as before, the lead chromate. Now we know this was something that was considered slightly soluble. It didn't break apart a great deal. So let's say we've already created a saturated solution of lead chromate. We've already established equilibrium between the solid and its dissolved ions. Now what would happen if we added lead nitrate? Lead nitrate is soluble in water. So think about adding the lead nitrate, and it starts breaking up into lead ions and nitrate ions. But wait, there's already lead ions in our solution. So remember the principle we talked about when we have equilibrium and we change a concentration. It was called Le Chatelier's principle. That's going to affect our equilibrium. We had an equilibrium, and now more lead ions are dissolving. Equilibrium is going to want to shift away from that change. Let's see what happens. So again, we had this equilibrium already established. Lead nitrate is very soluble in water. So it will start to increase the concentration of lead ions. And the system will want to undo that. It will want to minimize your change. So the equilibrium will shift away from that. We increased the concentration of one of our products. Our system's going to want to shift away towards the reactants. It's going to want to increase the concentration of our lead chromate. So, and this is a solid, so when the reaction shifts this way, it was at equilibrium. When it decides to start forming more of this, we'll start to see this precipitate out. If you remember the term precipitate, we combined two aqueous solutions, and we're going to see a solid start to form out of it. Here's a picture of that happening. Lead chromate is yellow in color. So here we've got an equilibrium solution. We have just lead chromate and water. Now some of it's sitting at the bottom as a solid because, as we saw, only a small amount will actually dissolve in the water. But in between here we've got a saturated solution. It contains lead ions and it contains chromate ions. And now we start dropping in some lead nitrate. And there's too many lead ions. As a result, the system shifts towards the reactants. It starts recombining some lead and some chromate ions to form additional lead chromate. But as it does so, that lead chromate is going to go back to the solid form. It can't be dissolved. It's forming away. It's forming the product. And so we've got more of this yellow solid forming and falling to the bottom. It's a very cool effect to watch. So in this example, the lead was our common ion. It just means it's an ion found in both compounds in the solution. And it acts to lower the solubility of one of the ionic compounds, and that's called the common ion effect. The solubility decreases when we have common ions. Let's try another example. Silver bromide is added to lenses in your glasses if you've got the fancy schmancy glasses that change color in the sunlight and darken. The reason they do that, this is actually pretty awesome, the silver bromide causes the lenses to darken in UV light. The KSP of silver bromide is 5 times 10 to the negative 13th. We want to know the concentration of the bromide ion in a 1 liter saturated solution of silver bromide, to which we then add some silver nitrate. So this up here, it's just a fun fact, but it's pretty cool. We're going to take that same compound that works in your eyeglass lenses, the silver bromide, and we are making a solution in equilibrium with it and water. Silver bromide would fall into our insoluble to slightly soluble compounds if we found it on that table. So we're going to form an equilibrium, and then we're going to add some silver nitrate, which would fall under the soluble category in our table. So what do we know? Well, we were given the KSP, the solubility product constant of silver bromide, and we know how much silver nitrate we're adding. We want to figure out the bromide ion concentration at equilibrium. So we've got our balanced reaction here, balanced equation for the dissolution, the dissolving of silver bromide in solution. And what we're going to do, we need to have just one unknown to solve any equation. We can't have both the silver and the bromide ions being unknown. So we know they have to be equal though, just like before. So we're going to let X be the equilibrium concentration of the bromide ion. Just some value X for bromide. And then our concentration of the silver ion would be X plus 0.2. The reason is we start originally in our saturated solution, these concentrations are equal. So they're both X. We've got X amount of both of these at equilibrium. But then when we add the silver nitrate, that's soluble, that splits into silver and nitrate ions, so it adds 0.02 moles of silver ion to our solution. So our new concentration after that addition of the silver ion is X, whatever it was before the addition, plus the 0.2 that came from this added compound. Now we need to write our equilibrium expression for the solubility product constant based off of our equation. That's the concentration of each of our products. We can substitute X for bromine. We're just going to let the concentration of the bromide ion be X. We'll solve this equation for X. To get X by itself, let me go back. To get X by itself, we just divide both sides by the silver ion concentration. So we've got the solubility product constant divided by the concentration of silver ions. We know this value, and we would substitute in the 0.020 plus X for the silver ion concentration. Now, let me pause you here. Because we could solve from here, it would be a bit more of a lengthy solution. But what would you do? Well, we would need to get this whole piece out of the denominator. And so we'd multiply both sides by 0.02 plus X. We'd have X times 0.02 plus X. We'd distribute that X out. We'd have 0.02X plus X squared equals a number. Ooh, that sounds like a quadratic equation. And we would treat it as a quadratic equation. We'd solve for X using the quadratic formula. So we could do that. We'd rather not. Alright, not huge fans of the quadratic formula over here. So maybe we can shortcut it. Let's see. Well, we know that KSP is pretty small. It's 5 times 10 to the negative 13th. That would tell us that there's more reactant than product. So, X is probably going to be pretty small, right? The concentration of silver ion, well, it's one of our products. It's probably not going to be that big compared with our initial concentration. Maybe we could just assume that it's so small that it won't matter. So small that adding it to 0.02 just works out to be insignificant in rounding, right? Think about adding 0.00002 to this number. Well, we get 0.02002, but if we round back to two significant figures, we've got the same number. So, hey, maybe we can leave that out. If we do so, if we make that assumption, we assume that when we add these together, we still would round to 0.02. Well, now we can easily solve this in our calculator. And we do. And we get that X, or the concentration of bromine ions, is equal to 2.5 times 10 to the negative 11th. And now we should go back and check and say, hey, is that small compared to 0.02? Is it small enough to not make a difference? And so we can go back and check and add that number to 0.02 and see that, oh yeah, we still would have rounded to 0.02, so it wouldn't have mattered. If we find out it wasn't small, technically we would need to go back and work through our quadratic equation the long way. But I think it was worth the effort to try and shortcut it because most of the time it will work out that that was a safe assumption. All right, so there is kind of a lot to these problems because you have to make some assumptions in order to be able to go from step to step. And so we solved for the concentration of the bromine ion. It makes sense that the addition of the silver nitrate would lower the concentration of the bromide ion because of the common ion silver. So let's go back to our equation just to talk through what happened there. We had this equilibrium. We dissolved silver nitrate, meaning all of a sudden there was more silver ions. We increased the concentration of our product. The system naturally would want to shift towards the reactants to mitigate our change, and so there would be less, some of those bromide ions would be used up in this reaction. The silver bromide would precipitate, we'd have fewer bromine ions left over. So the key here is that a precipitate will form if the product of the concentrations of the two ions in the mixture is greater than the solubility product constant value for the compound formed from the ions. And I'll show you what that looks like. So for example, as a solution of barium nitrate and sodium sulfate are mixed, we can see this white cloudy precipitate forming of barium sulfate. So let's see, does that always work? Let's say we're asked if a precipitate is going to form when we mix 1 liter of a 0.34 molar concentration sodium sulfate with 1 liter of a 0.002 molar concentration of barium nitrate. We're given the KSP for barium sulfate, and so let's start by writing out an equation for those. Never mind. We've got these two mixtures. The concentration of each is going to be half because the two 1 liter solutions are combined to make one 2 liter solution, right? We combine 1 liter of this, 1 liter of this. Now we have 2 liters of the mixed. We had 0.3 moles in 1 liter. Now we have 0.03 moles in 1 liter. Now we have 0.03 moles in 2 liters. So we have half the concentration of each of these. The volume is doubled. So again, that's just another way to think about the concentration being halved. So we know the concentration of both of these after they're mixed. Let's multiply them. So we multiply the concentration of the barium, the concentration of the sulfite, because we're wondering if this precipitate forms. When we multiply the concentrations, we get 1.02 times 10 to the negative 5th. Let's compare that. Well, that number is bigger than their solubility product constant. That means, remember, the solubility product constant is products over reactants. We got a number that was too big. That means we have too many products right now. Our ions are the products. There's too many of them. So the reaction wants to shift towards the reactants to get back towards this smaller number. It wants to make less product, more reactant, and so we will see a precipitate form. Again, these problems are probably the hardest in the unit just because you really have to understand the concept to be able to apply the math. So what we were looking for here overall was we want to compare these concentrations when they're mixed to see if there's too much product or too much reactant. And when we multiply their concentrations to get a number, we got a number that was bigger than K. That means there's too many products. We'll make more reactant. Our reactant was the solid, so we see a precipitate. If we got a number that was smaller than K, that would mean there's too much reactant. More of it's going to form, more of it's going to dissolve. We won't see a precipitate. We'll just see more things dissolving. So between this one and, again, that previous example, you should be able to kind of use these as a guide for any homework problems. You can use the ICE tables discussed in the previous lesson, again, to keep this information straight and everything in the right place as well, if you find that helpful. Again, I think it's a great tool. And just use these examples in the slides to work through the problems. That way you make sure you don't leave out any steps. You'll be reminded of being able to sometimes make this assumption to make your problem easier and avoid a quadratic formula. Alright, so give those homework problems a try. These are the problems in the 18.4 section. And then let me know if you have any questions.